Okay, so maybe we should begin. It's great to see so many people avoiding the work of their offices and taking advantage to learn about something that seems to interest a lot of people. So Stephan Rasp is a PhD student, kind of working on his second PhD, but he forgot to collect the first one along the way on some aspects of machine and deep learning. His other work actually is in numerical weather prediction. So he's done some work on one thing that I find quite interesting is how convection, when you have large-scale storms, you have moist air that goes up a slant, and so it follows this moist adiabat and slantwise convection. But when we do the very high-resolution simulations, you see lots of convective towers. So if you look in the HGCP simulations, you see lots of vigorous convective overturning. So he was spent part of his master's research looking at that question. He's been evaluating stochastic parameterizations of convection and theories of aggregation and cumulus mass fluxes, also as part of the first part of his PhD. And sort of as a hobby, he kind of taught himself machine learning, as I understand it, and has been sort of picking on that, and has been really at the forefront of what's a real wave in the atmospherics part of the earth sciences in terms of machine learning approaches to representing physical phenomena in the atmosphere. So he kind of found his way to UC Irvine, where he worked on this paper with these two characters who we'll tell you about in a second, I guess. And we invited him here along with another guy, Yanni Uval, who will be here just to have a little brainstorming session about ways in which we can use our efforts to do really high global cloud resolving, high resolution global cloud resolving modeling, how we can use that to advance machine learning approaches. So the idea was to have a workshop, but Stephan volunteered to give a little overview talk on some of the stuff that's happening. So this wasn't really a planned seminar, we just kind of came up with the idea. He suggested, oh, I could give a seminar. So we threw this together, and so here he is, and yeah, so the floor is yours for the next 45 minutes.
Thanks a lot, and thanks for the invitation. So yeah, I'll talk about machine learning to parameterize subgroup processes. And I should introduce these two guys. So I spent February to June at UC Irvine, and Mike Pritchard was so kind to host me there. And we also worked together with Pierre Gentine, and I think he's been here. He was here just a few months ago, I think. So it turns out that this is kind of a hot topic in the atmospheric science community right now. And the way I found out that this was a hot topic was after I started working on it is at a recent conference. This was a conference at Caltech, organized by Tapio Schneider on the future of Earth system modeling. And this was sort of an invite-only event. And being an invite-only event, I of course was not invited, but my supervisor was, and I kind of begged to be there, and so I was allowed to be there for at least one day. And so I looked at the program, and so this is our work. This is Mike presenting what we did. And so then I noted that the talks before all had very similar titles. So all of them are on machine learning for parameterization. And I actually got another reminder just a few hours ago that this is kind of a hot topic. I got a Google Scholar citation alert. And it turns out that the numerical weather prediction community, so these are two guys from ECMWF, are also thinking about this sort of stuff. Okay, so the question is then, why are people thinking about this now, and what's wrong with the way we're doing parameterization currently? So we atmospheric scientists are really kind of screwed. We have these models that have grid spacings, on the order of 100 kilometers, but sort of all of the interesting and important physics happens below the grid scale. So clouds can be as small as a few hundred meters, yet I don't think I need to tell you that they're absolutely crucial to model the Earth system and figure out what's going on with climate change. So the way people traditionally deal with this is they build simplified models of the system in question. And these are the so-called parameterizations. So parameterization takes as an input the resolved scale variables, so for example, your temperature profile, your humidity profile, and it computes, it spits out the subgrid tendencies due to that particular process. And normally you split up the processes. So you have a parameterization for convection, you have a parameterization for turbulence, and so on. And so a quick disclaimer here. I know that a lot of people in this room deal with other components of the Earth system, the land or the ocean, and I'm going to ignore all of that. So we're going to focus on the atmosphere solely. Sorry about that. Now, this sounds like a pretty good system. So where's the problem? The problem, forgot to say, this is of course feeds back with the resolved dynamics, and this is basically a climate model. So the problem lies in this step. How do you reduce the incredible nonlinear complexity of the real world to a simple set of equations that you can then code up in your climate model? And this problem has sort of befuddled scientists for a long time now. And because this problem turns out to be so difficult, current parameterizations are still imperfect. And because parameterizations are imperfect, climate models still have problems. So I'm just going to throw out a few of those. So models still have problems representing the intertropical convergence zone. They have problems with tropical waves. So for example, the Mendelian oscillation, really important intraseasonal variability, is often missing. They have problems representing precipitation extremes, so the extreme weather that we actually really care about. And the land-atmosphere coupling is terrible in some of these parameterized convection models. So these are just some examples of biases. But the sort of uncertainty that this introduces matters on a much larger scale. It matters because it causes a lot of uncertainty in modeling the future climates. And so you might have seen this before. This is a graph that I think really illustrates this uncertainty. What's shown here is the change in the cloud radiative effect in the top row and the change in precipitation for a 4K warming in the sea surface temperature. These are aquaplanet runs for 4 current climate models. And the details don't matter. What matters is that they all vary wildly. And now, this uncertainty then also limits our ability to make policy decisions. So one quantity that people always look for in climate models is the equilibrium climate sensitivity. How much warmer does it get for a doubling in the CO2 concentrations? So this is the equilibrium climate sensitivity, plotted for 30 state-of-the-art climate models. And you can see it ranges from about 2 degrees to almost up to 5 degrees. Now, conversely, this also means there's a huge uncertainty about how much more CO2 we can emit to the atmosphere before we cross a certain threshold, for example, the 2-degree threshold that everybody talks about. Now, what this is scattered against is the low cloud reflectance change. So this is how much does the low cloud cover change, which of course all happens below the grid scale of climate models as a response to this CO2 doubling. And the correlation is really striking. So what this tells us is that a bulk of this uncertainty really comes from the representation of these subgrid clouds. And so we can say then, for better climate predictions, we need a better representation of clouds. Now, one way to get a better representation of clouds is to use high-resolution simulations. So you probably will have seen this visualization before. It's done by Matthias Brück. What this shows is an icon simulation with 2.5 kilometer resolution over the Atlantic. And you can see all these fine details in the water vapor profile here. And what I also find really impressive are these squall lines that parameterized convection models really struggle with. So as you go down from your typical climate model grid spacing to smaller scales, you cross certain thresholds. And the first one is at around 4 kilometer, because at that resolution, it becomes possible to sort of resolve deep convection. And that has a number of benefits. For example, a better land-atmosphere coupling, better extreme weather representation, and a better coupling of the convective heating to the dynamics. And that really matters for representing the Mendelian oscillation or the intertropical convergence zone. When you go down in scale another order of magnitude, you come into the range of large eddy simulations. There you resolve the most important turbulent eddies and also shallow clouds, which you have seen as so important for the cloud radiation feedback. The problem is these simulations are really expensive, and this figure illustrates this. What's plotted here is the evolution of horizontal resolution for different sorts of climate models. The filled circles are atmosphere-only models. The empty circles are atmosphere-ocean models, and the diamonds are Earth system models, so the ones with the most complexity. Also plotted here is, by the way, the computer performance, which still follows Moore's law approximately. Now, This is the resolution we sort of want to get at, around 1 kilometer, right? So if we extrapolate, we might think that for atmosphere-only models, you know, we might be able to get there within a decade or two, or maybe some people in this room might think earlier. If we want to model the full Earth system, though, you know, we might have to wait quite a long time, and that's sort of unsatisfying. We don't want to wait this long, we cannot wait this long. And so, what to do? And I want to propose a potential shortcut, and that's machine learning. Okay, so what is machine learning? The definition of machine learning is it's algorithms that learn from data but are not explicitly programmed. So this is sort of the reverse approach from your sort of typical parameterization, which are explicitly programmed based on physical understanding. The basic idea that I want to talk about for most of this talk goes something like this. This is your typical workflow. What if instead we ran short-term, high-resolution simulations to train a machine learning algorithm that then replaces the original parameterization? And so this is what I want to explore. But we're going to have to take a hard cut in this presentation now, because the machine learning algorithm we're using is a neural network. And so I'm going to try my best to explain to you what a neural network is and what it does in the next few minutes in one slide. Okay, so what's a neural network? A neural network consists of nodes. That's each one of these circles, and each of these nodes holds a number, a value. And these nodes are arranged in layers. So this, for example, is the first layer, it's the input layer. So these are all the numbers that you put into the neural network. The next layer then, all of the nodes in this next layer are weighted sums of all the values in the previous layer's nodes, plus a bias term. So each one of these connections here is associated with a weight. So you end up, to go from one node to the next, you end up with a weight matrix and a bias vector. And you can repeat this operation. To get to the next node, you have another set of weights and biases. And you can do this over and over again until you get to your output layer, which then represents all the values that you want the neural network to produce. Okay, so some of you might be thinking now, all right, that's just a bunch of linear matrix multiplications stacked on top of each other. So that's really no different than sort of linear regression. And you're right, because we forgot the neural in the neural network. What this means is that we have some nonlinearity in there. And for this, all of the hidden layers, so these are the layers in between the input layer and the output layer, all of the nodes here are passed through a nonlinear activation function. So that's a simple nonlinear function that gets applied to all of the values in these hidden layer nodes. And this function can be really very simple. In fact, the one that's most commonly used, and the one that we're also using, is called a rectified linear unit, and it looks like this. In other words, you set all the negative values to 0. Now, it turns out that with a combination of these very simple nonlinear functions, you can actually model very complex nonlinear functions. And if this sounds a little bit like magic to you, you're probably right. And I don't think anybody really understands why this property is happening. And if you're interested in finding out more, there's a great online resource. It's this online book here by Michael Nielsen. And in chapter 4, he has a visual representation that neural networks can approximate any nonlinear function. That should help you. All right, we're just going to assume that it's true. So think of this as linear regression, but nonlinear. But the question is, of course, how do you know what the weights and biases should be, right? And for this, we need a training data set. So that's a data set where you know what the outputs should be for a given input. So you initialize your neural network with random weights and biases, and of course it's going to produce garbage in the beginning. And you compare it to the training data, so what should come out of the neural network, and you compute a so-called loss function. That's sort of an error metric that's lower if the neural network provides better predictions. And then you figure out how do you have to change these weights and biases in order to lower this loss. And you do this by simply differentiating and taking a little step down the gradient. For this reason, this algorithm is called gradient descent. Okay, So that's basically the entirety of what a neural network is. So it's really just a bunch of matrix multiplications. Okay, if we want to apply this now to our problem, in the input we have the same input that a normal parameterization would have. So these are resolved variables, the temperature profile, the humidity profile, and we can simply stack these on top of each other to get one long vector. On the output side, we want to produce the subgrid tendencies, and these are produced for our training data from the high resolution simulations. Okay, so this is what we're gonna try now. But I ask another question in the beginning. Why is now the time that people are looking at this? And I think there's two developments going on. The first development is sort of on the Earth system observation and modeling side. We now have an unbelievable wealth of data that's coming from satellite observations and so forth. And we also have the capability now to run high resolution simulations for reasonable amounts of time. On the deep learning side, we have an explosion of development. So I don't know if you've seen this before. These are faces generated entirely from scratch from a neural network. So you can see it a little bit. It looks a little weird. But I think the much more important development that all this development in deep learning has brought is that we now have the computational tools to program up neural networks quickly and efficiently. And so in fact, what you see here is the entirety of the neural network code used for what I'm going to show you. So these two developments here, you know, if you bring them together, there's sort of this realm of unexplored possibility. And we wanted to test one approach in this realm, and this is what we're going to talk about now. So let's talk specifics. This is now our setup. For the base model that we're using sort of as our training and reference model, we use the super parameterized community atmosphere model. If you haven't heard about super parameterization, it's sort of a step in between a global cloud resolving model and your general circulation model. Because in each global grid column, you have a 2D cloud resolving model that resolves convection and feeds back the convective tendencies to the global grid. And it turns out that you capture a lot of the benefits of global cloud resolving models at a reduced cost. So for example, a better IPCC structure, better representation of the tropical waves, and you get the precipitation extremes better. Now we run this in an idealized aquaplanet setup, and we generate 1 year of training data for the neural network. And that ends up being about 140 million training samples. So that's every grid column for every half hour for an entire year. It adds up to about 140 million. So this is our training data. Now, the neural network takes as an input the temperature profile, the specific humidity profile, surface pressure, the surface fluxes, and the incoming solar radiation. And it produces as an output the convective and radiative heating tendencies, the convective moistening tendency, the radiative fluxes, both short wave and long wave at the top of atmosphere and surface, and the precipitation. Note, we're not using cloud water in the input or the output. This is a simplification to reduce the complexities of the problem, and I'll talk more about this later, why we're doing this, and what effect this has. The neural network itself has 9 hidden layers, and each of these hidden layers has 256 nodes. That ends up being about 500,000 parameters. Now, why did we choose this specific design for the neural network? There's sort of 2 ways in which you can design a neural network. The first one, you can design it in a shallow way. That means you have few hidden layers between your input and output layers, but they have a lot of nodes. For the same number of nodes, you could design it in a deep way, where you have a lot of hidden layers that do not have as many nodes. And it turns out that this deep architecture is a lot better. And so we tried out a few different architectures here. And so this is the mean squared error. So lower is better. And first of all, you can see as you increase the complexity of the neural network, as you increase how big the neural network is, your error goes down. But then you can also see for the same number of parameters, of free parameters that you have to estimate, as you go from a shallow neural network to a deep neural network, you get a better fit to your training data. Okay. These deep architectures have another major advantage. And we came to appreciate that advantage when we actually took the big leap. So we've trained a neural network now with our high resolution simulation. But of course the question is, what happens if you then actually implement it in the climate model and let it feed back with the resolved dynamics? And it turns out the big challenge here is stability. Because what can happen is, and others have tried this before and failed for this reason, is that you develop unstable feedbacks. So where the output of the neural network in one time step feeds back to its input in the next time step, and you can either get your predictions to explode or develop really unrealistic artifacts. Now, we observed the same thing when we used a shallow neural network, but it turns out that deep neural networks are much more stable, and we did not see any of these failures when we used deep neural networks. Okay, so we then implemented it into the climate model, and technically this works like this. You compute your weights and biases in Python, so you go from something that looks nice and pretty like this, and then you copy them out, load them into Fortran, and then you end up with something like this. It's ugly, and even uglier because I don't know how to code Fortran well. In any case, the big selling factor right up front, the neural network is just a bunch of matrix multiplications. That means it's really fast. It's 20 times faster than our superparameterization, and it's even 8 times faster than the traditional parameterization setup. And the key thing to remember here is that the neural network would not become any slower if you trained it with really expensive training data. Okay, so we were then able to run 5-year prognostic simulations that had a stable climate, and we even ran a 50-year simulation that was also stable. So that's good news, but of course you're gonna ask, well, how good is it? So that's what we're gonna look at now. And first up, the mean climate. So these figures that we're going to show you work something like this. You have the South Pole to the North Pole against height. Because we're solely invariant in our aquaplanet setup, we can just average out that dimension, and these are 5-year means. What's shown here is the subgrid heating tendency, the mean subgrid heating tendency for the superparameterization, so this is sort of our reference. Then for the neural network, so these should be the same. And then also we ran a control version where we ran the model with the traditional parameterization setup. Now, don't overinterpret these results because this setup is actually kind of an old setup, so it's not state of the art. It more serves as a reference point to judge differences between these two. So you can see there's good agreement, so that's good. And you can also see that the control version has this strong double ITCZ bias. So this is the direct output of the neural network. If we then look at the resulting mean state, what's shown here is the absolute temperature state of the SPChem and the differences to the neural network and the control. And if we focus only on the troposphere, you can see that the temperature deviations are way below 1 Kelvin. And specific humidity and the wind are also really well represented. The only problem that we're having is the temperature in the stratosphere. And we're not too worried about this, and there's 2 reasons for this. First of all, the model that we're using has a really low resolution in the stratosphere, so it's not good anyway. And second of all, the model is really sensitive in the stratosphere, and you can see that the differences in the control version are even larger. So it's not ideal, but could be worse. Then also the mean precipitation. Go on.
Quick question. So if you train your network on the parameterized course, outdated model, it will simply reproduce that one. In that sense, you don't even need that other IPCC because you could also reproduce that one.
Sorry, I didn't really get.
If you would train your network on the bad solution,
Yeah.
reproduce the bad solution.
Well, you would hope so, yeah. I mean, the big question is, so yeah, I'm just showing this as a reference. The key question is, does it reproduce what it's trained on? And I mean, it's not obvious that it does because it's now in a system where it freely interacts with another component, right? So you would hope that it does, and it does, but as I said, people have tried this before and it did not work because the neural network did not behave in a way that is stable, right? So, I mean, it does what we hope it does, but it's not trivial. At least I failed many times, so maybe I'm just dumb, but yeah. Okay. So, as you just said, the mean climate is pretty well reproduced. So that's good. But in climate modeling, we're not only concerned about the mean, we're also concerned about the variability. The first thing we want to look at here is the precipitation distribution. And here you see a typical bias for parameterized convection is that you don't have enough precipitation extremes. The neural network reproduces the precipitation extremes remarkably well. A more difficult test maybe is the tropical wave spectrum, because tropical waves depend crucially on the interplay between the subgrid convective heating and the resolved dynamics. And so what we can see here is that we also get a pretty good agreement. We have sort of an MJO-like blob here. Remember, this is a pretty idealized atmosphere and some Kelvin waves, and they might be slightly weaker in the neural network implementation, but still the overall fit is quite good.
Your big stuff in that, but that's probably tropical storms.
These?
You have more?
I don't know if these results are significant or if the column map just shows these up as, okay, so one area where we do see some differences if we look at the variability of the subgrid heating. So that's the direct output of the neural network. How variable is that? Well, that's what's plotted here. And there's two issues that we see. First of all, we see that we have a lack of variability in the boundary layer. And we think this is because the superparameterization is in a way stochastic. It's not really, but in a way it produces sort of noisy outputs. And if the neural network during its training is faced with these noisy outputs, sort of uncertainty what it should produce, all it's trying to do is reduce its mean error. And so it's going to give you sort of an average solution. And so we have less variability. The other issue is that even for the control cam, you see there's a maximum here at the shallow Clyde level, and that's missing in our neural network runs. And that also makes sense because, as I told you in the beginning, we're omitting cloud water, right? So the neural network doesn't really know anything about clouds, and that's a direct consequence of this. So here we see some deficiencies, which we can explain though. But overall, the climate variability and the extreme weather seem to be pretty accurately captured. So these are good news. But there's two questions that people always ask when hearing about this, and they ask it for a good reason. So the first one is, does the neural network conserve energy? Okay, that's of course an absolutely crucial question to ask. And we're going to first look at this in a global context. This is the global mean energy and a global mean moisture for these 5-year simulations. And you can see some scatter because actually we don't, in our aquaplanet setup, conserve energy exactly, right? The surface is not really interacting. So, but what we can see is that the neural network produces a stable climate, so we see no drift, and also the scatter is reasonable compared to the other simulations. Okay, but energy conservation doesn't only have to be true globally, but also for each grid column, since we don't have any communication between grid columns. And so what we plotted here is the column moist static energy conservation. So this shows the column integral moisture tendency against the column integral temperature tendency in energy units, and we subtract the surface fluxes and the fluxes at the top of atmosphere. So these should approximately balance, because again, we're omitting cloud and ice, cloud water and ice. And so you can see there's a little bit of scatter even for the superparameterization, but pretty accurate. And the neural network also reproduces this relationship between the variables pretty accurately. There's a little bit of scatter that you can see here, but most importantly, we have no outliers. So energy conservation is never violated badly. So that's really encouraging because we never told the neural network anything about energy. So in some way, and I say this cautiously, the neural network has sort of learned some sort of approximate energy conservation, whatever that might mean. Okay. Question number 2, can a neural network generalize to new climates? Okay. First test that we run is we perturb the sea surface temperatures with a zonal wave number 1 perturbations of 3 Kelvin amplitude. And remember, this is the neural network that's trained on the reference climate only, so zonally symmetric. So what's shown here now is the vertically integrated heating. And so you develop a Walker circulation here with the convective maximum concentrated at the warm pool. And the neural network does a really good job at reproducing this. We can also look at the vertically integrated temperature difference. And again, we see that the temperature deviations are within 1 Kelvin. So as a result, we can say that generalization seems to be possible to some degree. But what if we do a global warming experiment? So this is a much more extreme test. What if we globally increase the sea surface temperatures? Okay, so first we'll look at the neural network that was trained with the reference sea surface temperatures only. So that's what you've seen so far. And you've already also seen these figures, so where we see a pretty good agreement. What if we increase the sea surface temperatures by 4 Kelvin now? And here we see some problems popping up. So first of all, we see some weird heating patterns here at the equator, and that's of course where it's warmer than what the neural network has ever seen during training. And then if we look at the resulting temperature state, I mean, it's just not very good. We can do the reverse experiment. What if we train the neural network with the warm climate, the +4 climate only? So that's now what we've shown here. This is the neural network trained with the warm climate and also run with the warm climate. And you can see again the simulations are pretty good. If we go back now to our reference state, you know, this looks all right, but then if we look at the temperature state, we see now the problems popping up at the poles, where it's now colder than what the neural network has ever seen during training, okay? All right. The final experiment we ran is, what if we trained a neural network with both the reference climate and the warm climate, okay? And here we now see that we get good agreement for both states and also temperature deviations that are in a reasonable range. And this also applies for all the climates in between. So we also had a +1K, +2K, +3K run, and they also all look pretty good. So we can say then that the neural network struggles to extrapolate beyond the climates that is seen during training, but it manages to interpolate between extremes. All right, so let's now sum up our work. Okay, so what we did is we trained a neural network with a high resolution simulation to replace the traditional parameterization in a climate model. And we've seen that our neural network simulations reproduce the key features of the high resolution simulation. So most notably a stable climate, the precipitation extremes, and the tropical wave spectrum. The big selling point is it's much faster than the high resolution simulations and will stay faster even if you use really expensive training data. We see that energy conservation is learned to some degree, right? Whatever that might mean. And finally, we see that the neural network generalizes to some degree, but it fails for the global warming experiments. Now, one note about that, I think these global warming experiments are sort of exacerbated in our setup because we have a very homogeneous training climate, right? We have no seasons, we have this aquaplanet setup, so everything's always the same. So even a subtle warming will be immediately beyond the training regime. So if you train with a realistic climate where you have a lot more variability, this might not show up quite as much. But of course, this is still, you know, something that we should worry about. Okay, so this is basically what we did. And now for the end of this talk, I'm gonna work my way back up to the big picture. And the first step is, well, I told you in the beginning that other people were working on this too. So what did they actually do? So first of all, Chris Burton and his postdoc, they tried to basically do what we did, pretty similar setup, and they failed because, I think they failed because they used a shallow neural network and they ran into stability issues. Now they actually tried to come up with a different solution rather than using a deep neural network. Their solution was to change the loss function. So that's the function that you try to lower as you train your neural network. And they used a time average loss function where they would average the loss over many time steps that gave him a more stable solution, but they were only able to run a single column model test in the end. Paula Gorman at MIT, also very similar experimental setup. The big difference is he used a different machine learning algorithm. He used a random forest. So I'll try to, in 2 sentences, explain what a random forest is. a random forest is an ensemble of decision trees, okay? And the decision tree splits your data into finer and finer branches and makes predictions based on the splits. So if you don't understand this now, I'm sorry, but Google it if you're interested. Now, this approach has some advantages and some disadvantages. First of all, the advantages. Because a random forest is basically a lookup into your training data, it tries to find the closest match in the training data. It also has all the properties that your training data has. For example, energy conservation and stability. So these are guaranteed. On the other hand, it is just a lookup, whereas a neural network learns a function from the input to the output. So that's maybe more of a conceptual disadvantage. A very real disadvantage is that there's computational limitations for these random forests because you have to sort of fit all your training data into RAM, and also at prediction time they're much slower than a neural network. And so he was actually only able to use 1% of the training data that we were able to use. Okay, so these sort of machine learning parameterizations, they seem feasible, but there's still a lot of challenges to overcome. And the first one is, of course, all of these studies, also the ones that I showed you previously, were done in very idealized setups. So Aquaplanet and so on. Now we need to extend this approach to more realistic setups, and on the way there will be challenges with stability and physical constraints. So I told you that we didn't use Cloudwater, and also these previous studies, they didn't use Cloudwater because with Cloudwater you run into problems with preserving a positive mass concentration, and it turns out to be not that trivial to resolve these. So there will be some challenges that still have to be overcome as we go to the real Earth system. Now, of course, we also would like to use better training data. You know, the superparameterization is sort of a compromise, but we would like to use real global 3D cloud resolving models. And the final challenge that I haven't talked about really is tuning, right? I mean, these neural networks, what I've shown, they reproduce pretty well what the training data did, but they're still not perfect. And what do you do now? Because you cannot really tune a neural network. A neural network has hundreds of thousands of parameters. You don't even know where to start. And so I think for an effective implementation in the future of these machine learning parameterization, some sort of online training is required where you run a high-resolution simulation in parallel with your machine learning algorithm and update the machine learning algorithm as you run a prognostic model forecast. And that, of course, is technically quite challenging, and don't ask me about the specifics about this graphs, where the arrows should go, because it's actually not that trivial to do, I think. Okay. Let's go one step further to the big picture. So the approach that I've shown and that these other people tried is something that I call sort of one algorithm to rule them all, right? So we have our high resolution data and we train one machine learning parameterization to represent all of the subgroup processes. You could take a different approach. What if you try to learn parameters or parametric functions in an existing framework? So, for example, if this is a convection parameterization, you could learn the entrainment rate or a function for the entrainment rate. Now, there's advantages and disadvantages to both. So, if you have this one algorithm to rule them all approach, and your training data captures interactions between processes, for example, clouds and radiation, then your algorithm will also capture these relations. So that's pretty great. It comes for free. And of course, they do not rely on sort of a heuristic parameterization design where you already might bake in some biases. On the other hand, if you learn in an existing framework, you know that the physics that you do know are obeyed. So you will not run into problems with energy conservation and so on. You make sure that this is obeyed. And also, this might give you better generalization capabilities for warmer or colder climates. And these parameterizations might be more interpretable. And I think this speaks to a larger sort of divide in why we even do climate and weather modeling. I think there's like two extreme ends. On the one hand, particularly numerical weather prediction, you just try to get the best predictions. And you might not really care how you get to these best predictions. And then an approach like this, if it's better, might be totally warranted. On the other hand, a lot of you here in this room, you do climate modeling because you want to gain an understanding about the system you're modeling. And for this sort of one algorithm to rule them all approach might not be the most interpretable option. Okay. Final slide, the really big picture, right? So what I've presented today is sort of a small part in the quest to efficiently use high-resolution simulations and observations. And you might have noticed that I say observations here, but I didn't really talk about observations. All we did is try to use high-resolution simulations. And the reason for this is observations are really hard. Now, in numerical weather prediction, there's an entire field that's just concerned about how to get the best state estimate from the observations that you have, called data assimilation, right? But all the extensions of data assimilation to estimating parameters have sort of been unsatisfying so far. And so I think finding good algorithms to learn from observations is really a key challenge. Then on the other side, of course, there's all this development in deep learning. So there's a lot going on and they can be pretty confusing. But I think, from what I can tell, that there's actually a lot of overlap between the algorithms in data assimilation and deep learning. And so the problem is sort of that these two communities speak completely different languages. They probably don't even know of each other. Well, everybody probably knows about the deep learning community, but I somehow doubt that many deep learning people really know about data assimilation, right? And so I think finding sort of the intersection in these fields could be a really promising approach. And then the last thing I sort of want to say is, I do by no means want to suggest that sort of the traditional model development should be abandoned, right? I think physical model development has gotten us very far and it will get us further in the future. And so I think sort of a synergy between these approaches is where the real potential lies. Okay, so this is basically it. One final thing, okay? So you might think, okay, this sounds pretty cool. And actually, it is really cool because deep learning is a really flexible approach. You can do a lot of other things with it. You can analyze your image data, you can post-process your model output, and I'll let you in on the secret. It's also pretty easy, right? Because what you've seen, it's just a bunch of matrix multiplications, and it's a few lines of code, so it's no magic. And there's a lot of great resources out there on how to learn about deep learning, neural networks, machine learning, and I wrote a blog post about it if you're interested. I can only recommend looking into this if you're interested. I think it can be applied to many areas of our science field at the moment. And then because nobody's done it before, there might be some low-hanging fruit. So with that, thanks.